80 miles off the coast of England, buried beneath the muddy floor of the North Sea, scientists just confirmed something that had been argued about for more than 20 years. And the answer means a giant space rock once triggered a wave taller than a 30-story skyscraper, close enough to Britain that it would have reshaped the entire region in a matter of minutes. This is not science fiction. This is confirmed, published, peer-reviewed research, and it just rewrote a chapter of Earth's violent history that most people never even knew existed. Back in 2002, geologists studying underground survey data noticed something strange hiding beneath the seabed of the southern North Sea. A massive circular structure, nearly 2 miles wide, sitting roughly 700 meters below the muddy floor of the ocean. It had a distinctive bowl shape. It had a raised central peak. It even had strange ring-like fractures circling outward from its center, almost like ripples frozen in solid rock. To anyone familiar with impact craters, this shape looked instantly familiar. But identifying something that looks like a crater and actually proving it is a crater turned out to be two very different challenges. For more than 20 years, scientists were bitterly divided over what this bizarre structure actually was. One group of researchers argued it was created by a massive asteroid or comet slamming into the seabed millions of years ago. Another group pushed back hard, insisting the same circular shape could easily be explained by far more mundane geological processes, like shifting underground salt deposits slowly collapsing over time, or ancient volcanic activity punching through the crust from below. Both explanations could theoretically produce a circular depression. Without direct physical proof, there was simply no way to settle the argument with total confidence. That argument finally ended when a team of researchers led by scientists at Heriot-Watt University in Edinburgh went back to the data, with fresh eyes and far more advanced tools than had ever been available before. Using high-resolution three-dimensional seismic imaging, the team was able to construct an incredibly detailed picture of the crater's internal structure, something previous studies simply did not have access to. This new imaging revealed layers of damage and deformation deep beneath the seafloor that closely matched the exact kind of destruction caused by an object slamming into the ground at extreme velocity, rather than gradual geological processes playing out over thousands of years. But seismic imaging alone was not enough to settle a debate this old. To find truly definitive proof, researchers needed physical evidence, something they could hold in their hands and examine under a microscope. That is exactly what they found buried inside drill cuttings, recovered from the site. Hidden within these tiny rock samples were something scientists call shocked minerals, microscopic grains bearing distinctive deformation patterns that can only be created by the extreme pressures generated during a genuine hypervelocity impact. This is not the kind of damage volcanic activity or shifting salt deposits can replicate. Shocked minerals like these are essentially a fingerprint left behind by violence from outer space. According to one of the researchers involved in modeling the impact, this discovery finally represented what he called the silver bullet, the single piece of undeniable evidence needed to settle a scientific argument that had dragged on for more than 2 decades. When you combine detailed seismic imaging with actual physical proof recovered from inside the crater itself, you get a level of certainty that simply was not possible using older survey techniques from years past. So what actually happened here, all those millions of years ago? According to the new research, an asteroid roughly 160 meters wide, about the length of 1.5 football fields, slammed into the shallow seabed of what is now the southern North Sea, somewhere between 43 and 46 million years ago. At the moment of impact, this was not empty ocean the way we might imagine today. The region was covered by a relatively shallow sea, and the seafloor beneath it was made largely of chalk, a soft, porous type of rock, formed from the accumulated remains of ancient marine organisms. When that asteroid slammed into the chalky seabed at extreme velocity, the resulting explosion released an almost unimaginable amount of energy in a fraction of a second. The immediate impact vaporized rock, launched debris skyward, and sent violent shock waves radiating outward through the surrounding seafloor and water column. Within moments, the collision triggered a colossal tsunami, with wave heights estimated at over 100 meters, which is more than 330 feet from base to peak. To put that into perspective, that is roughly the height of a 30-story office building, generated instantly and sent racing outward across the ancient sea in every direction. If you are enjoying uncovering hidden mysteries buried right beneath our own planet's surface, go ahead and hit that like button right now. It genuinely helps this channel keep bringing you deep dives exactly like this one. Now here is where the story becomes even more scientifically fascinating. Researchers studying the crater discovered something unusual happening, specifically within the chalk located at the very center of the impact zone. Instead of behaving like a typical rocky crater, the intense heat generated by the collision appears to have caused something scientists call devolatilization, a chemical process where minerals inside the chalk rapidly release trapped gases when subjected to extreme temperatures. This devolatilization process may have caused the central raised peak of the crater, something normally seen rising upward after major impacts, to actually flatten out and collapse inward, leaving behind unusual pitted formations instead of a clean, simple peak. Model estimates suggest the volume of chalk that essentially vanished from this central region could represent a violent secondary burst of carbon dioxide gas, combined with scalding steam and pulverized rock fragments, erupting outward in the moments immediately following the initial asteroid strike. In other words, this was not simply one single violent event. It may have actually been two overlapping disasters occurring within seconds of each other. First, the raw, catastrophic force of an asteroid striking the seabed at extreme speed. Then, almost immediately afterward, a secondary chemical eruption triggered by intense heat interacting with the unique chalky composition of the local seafloor. Scientists believe this rare combination makes Silverpit noticeably stranger and considerably more scientifically valuable than a typical impact crater formed in solid, uniform rock. This detail matters far beyond simple curiosity. Researchers now believe that studying this unusual secondary eruption could offer valuable new insight into how marine impacts might trigger dangerous follow-up effects beyond the initial collision itself. If a future asteroid were ever to strike a similarly soft, chalky, or sediment-rich region of ocean floor anywhere on Earth, understanding this kind of secondary chemical eruption could become critically important for accurately predicting the full scope of potential damage, rather than just modeling the initial impact alone. Impact craters like this one are also remarkably rare on our planet, which is exactly what makes this confirmation so scientifically significant. Earth currently has around 200 confirmed impact craters located on land, alongside only a few dozen confirmed examples hidden beneath the world's oceans. That scarcity exists for a very specific reason. Powerful geological forces like erosion, sediment burial, and shifting tectonic plates gradually erase most evidence of ancient impacts over long stretches of geological time. Finding a crater this well preserved, sitting safely protected beneath layers of accumulated seafloor sediment for over 40 million years, offers researchers an extraordinarily rare opportunity to study exactly how these violent cosmic collisions actually unfold and evolve over deep geological time. This new confirmation also places Silverpit alongside some genuinely famous company within the world of known impact structures. Perhaps the most well-known comparison is Mexico's Chicxulub crater, the enormous impact site widely linked to the mass extinction event that wiped out the non-avian dinosaurs roughly 66 million years ago. While Silverpit is dramatically smaller in scale and far less catastrophic in its global consequences, both craters share that same unmistakable violent origin, offering scientists valuable comparative data points for understanding exactly how impacts of vastly different sizes reshape the landscapes and ecosystems around them. Silverpit joins another recently confirmed underwater crater as well, known as the Nader crater, discovered off the coast of West Africa. Just like Silverpit, the Nader crater spent years shrouded in scientific uncertainty before researchers were finally able to confirm its violent cosmic origin using similarly advanced imaging and sampling techniques. Together, these confirmations are gradually expanding our understanding of just how many hidden impact scars might still be waiting to be properly identified beneath the world's oceans, quietly hidden from view for tens of millions of years. There is something genuinely humbling about picturing this event as it may have actually unfolded, tens of millions of years before any human being ever existed to witness it. A relatively calm, shallow prehistoric sea stretching out where the modern North Sea sits today. Then, without warning, a chunk of rock traveling through space at incredible speed slams directly into the shallow seabed below. Within moments, an entire region is transformed by violent shock waves, vaporized rock, and a monstrous wave surging outward across the water, taller than most modern skyscrapers, racing toward distant, unsuspecting shorelines. Whatever ancient marine life existed in that region at the time would have had absolutely no warning and virtually no chance of survival. Anywhere near the immediate impact zone. This wasn't a slow, gradual disaster playing out over years or decades. It was violence measured in seconds and minutes, an instantaneous, catastrophic transformation of the local environment, followed by decades or even centuries of lingering ecological disruption, as the surrounding ecosystem slowly attempted to recover from such a devastating blow. What makes this discovery matter so much today goes far beyond simply satisfying scientific curiosity about ancient history. Understanding exactly how asteroid impacts behave when they strike shallow marine environments carries serious, real-world implications for modern planetary defense efforts. Roughly 70% of Earth's surface is covered by ocean, which means any future asteroid impact carries a genuinely significant chance of striking water rather than solid land. Until relatively recently, scientists had far fewer real-world examples to study when it came to understanding exactly how these marine impacts behave. how tsunamis generated by these impacts travel and dissipate, and how quickly the seafloor itself tends to collapse and stabilize in the chaotic aftermath of such a violent collision. Silverpit now offers researchers an unusually well-preserved, real-world case study for examining exactly these kinds of critical questions. By carefully studying how this particular crater formed, how its central structure ultimately collapsed, and how the surrounding tsunami likely propagated outward across the ancient sea, scientists can meaningfully refine their predictive models for future potential impact scenarios. This isn't just about understanding what happened millions of years ago in the distant past. It is about better protecting coastal communities and populated regions if humanity were ever unlucky enough to face a similar impact event happening again sometime in the future. If uncovering these kinds of hidden cosmic mysteries buried right beneath our own planet fascinates you, make sure you are subscribed, because there are so many more incredible discoveries just like this one still waiting to be explored right here on this channel. There is also something quietly poetic about how this particular mystery finally reached its resolution. For 20 years, the Silverpit structure sat quietly beneath layers of mud and rock, patiently waiting for scientific technology to finally advance far enough to reveal its true violent origin. It took sharper seismic imaging technology, more advanced computer modeling capable of accurately simulating hypervelocity impacts, and a lucky recommendation from a colleague working on a completely different impact site off the coast of West Africa, all coming together at exactly the right moment to finally crack this decades-old geological mystery wide open. And perhaps the most fascinating part of this entire story is simply this. We are walking across a planet that has been struck by violent cosmic impacts again and again throughout its incredibly long history. And in the vast majority of cases, we simply have no idea these events ever happened at all. Most of that ancient evidence has already been erased entirely by relentless erosion, buried beneath layers of shifting sediment, or completely destroyed by the slow, grinding movement of tectonic plates over unimaginable stretches of geological time. Silverpit survived that process purely by chance, protected and preserved beneath the North Sea for over 40 million years, patiently waiting for modern science to finally uncover the violent secret hidden deep beneath its muddy, unassuming surface. Let us go back and really examine why this particular debate managed to drag on for more than 2 decades, because the reasons behind that delay reveal something genuinely important about how difficult it actually is to study anything buried this deep beneath the ocean. Unlike craters found sitting on dry land where researchers can simply walk out with hammers, drills, and cameras to examine the rock directly, everything about Silverpit had to be studied indirectly through layers of seawater, mud, and solid rock, using nothing but sound waves, drilling equipment, and careful mathematical modeling. That alone made this one of the most challenging geological mysteries scientists have ever attempted to solve with total certainty. Seismic imaging works by sending sound waves down through the layers of the Earth and carefully measuring how those waves bounce back upward toward the surface. Different types of rock and different geological structures reflect sound in distinctly different ways, allowing scientists to build a rough picture of what lies beneath, similar to how a doctor might use an ultrasound to examine the inside of a patient's body without ever needing to physically open them up. But older seismic technology from the early 2000s, when Silverpit was first discovered, simply lacked the resolution. Needed to settle this argument once and for all. The images were suggestive, they were tantalizing, but they were not definitive. That changed dramatically with the arrival of far more advanced three-dimensional seismic surveying techniques, allowing researchers to construct astonishingly detailed models of the crater's internal structure, layer by layer, almost as if they were slicing the Earth open like a digital cake and examining each individual layer independently. This new level of detail revealed patterns of rock, deformation that lined up almost perfectly with computer simulations of exactly how a genuine hypervelocity impact should behave, providing the first, truly strong piece of the puzzle needed to finally settle this long-running scientific dispute. Still, even detailed imaging alone was not quite enough. Skilled skeptics could theoretically argue that unusual geological processes, however unlikely, might still produce similar patterns under specific, rare circumstances. This is precisely why the discovery of shocked mineral grains inside physical drill samples became such a critical turning point in this entire investigation. Shocked minerals are created only under conditions of truly extreme, near-instantaneous pressure, conditions that essentially only occur during genuine hypervelocity impacts or, in extraordinarily rare cases, powerful nuclear detonations. Finding these microscopic grains, embedded directly within physical rock samples, recovered from the crater, essentially closed the door on any remaining alternative explanations. It is worth pointing out just how remarkable it is that these tiny, shocked mineral grains survived at all, hidden inside rock samples that had already been sitting in storage for years, originally collected for entirely unrelated oil and gas exploration purposes. Sometimes, major scientific breakthroughs do not come from brand new expeditions or expensive new drilling operations. Sometimes they come from researchers taking a fresh, more careful look at material that had already been sitting quietly in storage facilities for years, waiting for someone to finally ask the right question and apply the right analytical technique. This detail also highlights something valuable about how modern scientific collaboration actually tends to work behind the scenes. According to researchers involved in this project, part of the motivation to revisit Silverpit came directly from a colleague working on the completely separate Nadir Crater investigation off the coast of West Africa, who suggested taking another careful look at this old, unresolved North Sea mystery using newly available techniques. Scientific progress rarely happens in complete isolation. It often emerges from researchers across different projects, different countries, and even different specialties, sharing insights, comparing notes, and occasionally pointing each other toward mysteries that deserve a fresh, updated investigation. Beyond simply confirming the crater's violent cosmic origin, this research also gives scientists an unusually detailed window into the specific timeline of events immediately following the initial asteroid strike. Based on careful computer modeling, researchers can now estimate not just the raw size and speed of the incoming asteroid, but the approximate height, speed, and reach of the resulting tsunami wave as it would have surged outward across the shallow prehistoric sea. These kinds of detailed reconstructions allow scientists to move beyond simply saying an impact happened, and instead begin accurately describing exactly how violent, how far-reaching, and how immediately destructive that impact truly was for the surrounding region. There's also an important, broader lesson embedded within this discovery about the sheer scale of geological time itself. 43 to 46 million years might sound almost meaningless to most people, an abstract number too large to properly picture in any meaningful way. But consider this. At the time this asteroid struck, our planet already looked dramatically different from the Earth we know today. Early primates existed, but nothing resembling modern humans had even begun to evolve yet. Entire mountain ranges we consider ancient and permanent today had not even fully formed. And yet, despite that almost incomprehensible span of time, this crater survived largely intact, hidden safely beneath layers of protective sediment, until modern scientific tools finally became advanced enough to properly examine it. That length of preservation also raises an intriguing question worth sitting with for a moment. If a violent, catastrophic impact, the event this significant could remain completely hidden and undetected for over 40 million years, right in a heavily surveyed, extensively studied region like the North Sea, an area covered by extensive oil and gas exploration activity for decades, how many similarly